So today we are going to start talking about fluid kinematics, and we are talking about another way to describe fluid motion. In this method, we employ the continuum hypothesis and consider fluids to be made up of fluid particles that kind of interact with each other and with their surroundings. So we can describe the flow of a fluid in terms of the motion of fluid particles rather than the individual molecules. So in other words, each point in space has a velocity. So our velocity, which is a vector here, is equal to have u component, v component, and w component, and each of and it means that, because if you look at the formula, for example, u has x, y, z, t in it, and the same as v and w, and it means that the velocity is a function of x, y, z, and t. So it means that it's a function of location and time. And this is the velocity magnitude because it's a vector. So this is how we know it from physics, that this is how we calculate the magnitude of velocity. So there are two ways to describe the fluid motion. The one is called Lagrangian method, and in this method, the individual fluid particles are tracked. This is like the method that we use in Bernoulli's, and it means that follow the individual fluid particles are tracked and follow the fluid as it moves. So let me write it down. So it's individual fluid particles are tracked. So another way, which is the Eulerian method, is a way of looking at fluid motion that focuses on specific locations in the space through which the fluid flows. As time passes, we can just track it. So so let me just write it down for you guys. So this is fluid properties are observed at points in a space, meaning in a fixed location, or observe fluid motion from a fixed location. And this one means that follow the fluid as it moves. So yeah, we can see the definition even through the figures. So this one right here which is just the function of time, is the Lagrangian method. And uh, the particle are moving, and we follow the particle. Mm. So this one right here, which is a function of time and location, is the Eulerian concept. So now let's go to the next section. So what we are talking here is that in general, fluid flow is three-dimensional, right? And it also unsteady, meaning time dependent, right? But it is possible for us to make some assumptions to simplify the problem. The first assumption that we can make is the two-dimensional flow. So in many situations, one of the velocity component may be small relative to the other components. This is how we can assume the two-dimensional flow. And we can assume the flow moves uniformly. If this is the case, so we can say that this is one-dimensional flow. And the steady flow, it's when it's not depend on time, and the velocity at a given point in a space doesn't vary with time, right? So we are going to show these assumptions in the problems that we solve, so you can easily understand it better. And here, when we say that it's not, vary with time, the velocity, it means that, for example, if we have dv over dt, because we say that it's not vary with time, right? Then it means that it's going to be zero. So now let's talk about some vocabs. These concepts, the streamline, straight line, and path line, are used to help in the visualization and analysis of the flow fields. So the streamline is a line that is everywhere tangent to the velocity field, right? So it means that if we look at this picture right here, for the two-dimensional flows, the slope of the streamline is going to be dy over dx, which is must equal to the tangent of the angle that the velocity vector makes with the x axis. So then it means that it's going to be equal to v over u, right? So the straight line are more of a laboratory tool than an analytical tool. So by using the instantaneous photographs of marked particles and that all pass through a given location in the flow field at some earlier time, so we can visualize the flow field. The path line, it can be used again in the laboratory, but this time we mark a fluid particle and dyeing it kinda a small dyeing a small fluid element, and then taking a time exposure photograph of its motion. So this is how we can visualize the flow field through path line. And this is important thing which said that if the flow is steady, all of these three definition mean the streamlines, streak line, and the path line, they are all coincide. So just uh, just remember that. Then we are going to talk about the acceleration field. So the acceleration is the time rate of the change of the particle velocity. And if we use the chain rule, so if we use the chain rule, we can figure it out the acceleration. For example, here we use the chain rule. So we have this one, and if we look at here, this dx dt right here is our u here, right? And then we have the dv and dx here. So this is how we just derive the acceleration out of the out of the velocity. So we kind of use the chain rule and the derivation to get the acceleration. So just this part here, it is dva over dt, right? And a is our particle, right? So we consider a particle and which moving, along a path line. So these terms right here, we call it a local acceleration. We call it local acceleration, and this whole part here, we call it convective acceleration. Because sometimes in the problem they might ask you not the total acceleration, they might tell you to find the local acceleration. So this is why we need to know the meaning. So then, and there is something else that I want you to pay attention to it. So here it's a Lagrangian description because it's just depends on time. So we just write it down as Lagrangian description. And right here, because we have time and location, this is our Eulerian description. Right, it means that we can use both of the method. Then going down to the shorthand notation, this is, we call it the material derivative operator. So let me just write it down. Yeah, I write it down here. So this is the material derivative operator, and then it means that, for example, right here, instead of these parentheses, I can use, for example, U, V, W, I don't know, T, E, or even pressure, or even density. So it means that we can use all of them instead of the parentheses. And then from here, okay, let me see. From here we have another operator that we call it a gradient, and this gradient, which is v dot gradient of something, means that we need to write it down as u times d of that variable over d of x plus v d of that variable, which is parentheses right here, and then w of d of that variable over z. So this is how we describe this operator right here, and also we call it this term. This is the, because it's all about the location, right? So this is a special derivative. So, and this is because of the change, and the change is due to the fluid motion. And then this one, this is the term, because now it depends on time, right? So this is the term of the unsteady effect. Steady effect. So then we also can write down the acceleration in vector notation. So in vector notation we have it, okay, if we call it a, and then we consider velocity as a vector, so this is how we can write down the vector notation as well, or even we can write it down as dv over dt plus v, and this is, I just told you, this is the gradient, right? So we can write it down as gradient of v, right? And also we know that this is this meaning of that operator, the material derivative operator, so we also can write it down as dv over dt, which is our acceleration, right? So the same thing as on top, but in vector notation. So now let's talk about how we can describe a fluid flow. So there are two approaches to describe and analyze the fluid flow. So the first one is a system, and the second one is a control volume. And the system is focused on a set of space, means a fixed mass, and the control volume is focused on a region of space, and which is surrounded by a control surface. So we call control volume as CV, and then the control surface, which is the boundaries of our control volume, is surface is CS. So for example, if we have a pipe, and then we consider an amount of mass that the fluid that passed the pipe, so at the initial time, the CV and our system is the same. But when at the, for example, if this is at time t, this is at time plus a small amount of time, then this fluid is moving, right? Then it means that next time the same amount of this is moving, right? But then the CV is still here. The CV is not changing. It's just like, let me choose another color. The CV is here, it's not moving, but the system is moving, which is that the red lines. So, or let me just take another example, which I think it's easier to understand the difference between the system and CV. Um, let's think about a piston. So let's say that we have a piston right here. So we have let's say we have a tank, and then we have a piston right here, right? So, and we consider the whatever fluid is in the container as our system, right? So this mass here is our system. So if I just push the piston down, let's say after some time we decide to push it down, this is our piston, right? We push it down, and then we have some amount of mass here, which we know that it's the exact mass here, right? But then this is now our system. So this is how we kind of describe it. But for the CV, for the control volume, for example, we have I don't know, a jet here, right? And then there are some fluid coming in, right? The fluid coming in, and then from here a flow go out, right? So if I have, let's say I have this control volume, and these are my control surface, right? So from here the fluid comes in, and then from here it goes out, but my control volume is always here, right? So this is the difference between the two. In general, when we analyzing a fluid flow, it is usually much easier to observe the region of the space occupied by CV. So it's not always, but most of the time it's easier to use the control volume. We're going to talk about it, I think, mostly in chapter 5. So we're going to go through it in details. So now we need to describe the laws governing fluid motion using both of the system. So to do that, we introduce one concept, which is the Reynolds transport theorem, which provides a way to shift from a system analysis to a control volume analysis. So if we consider B as is equal to Bm, we're gonna have, for example, and B is the quantity, M is mass, and B is a specific quantity, which is per mass, right? And for example, if we say that B is equal to Bm, right? Let's say our B is a half of mv2, right? And then we have B and M here. Now we're trying to find B, right? These two gonna cancel out, and then B is going to be half of V2, which is, we write it down here. So it means that we can instead of B put mv, or half of the m squared. And also I can change it a little bit. Let's say that we have m, right? And we know that m is volume per velocity. Always be careful that the volume is like the A inverse, right? So then in this way we couldn't confuse it with the velocity, which is v. So we have V over nu, which is we have V over nu. Sorry, I think I say velocity. It's nu. It's specific volume, right? So we have a specific volume, and then we also have our B here. Then it means that, and we know that the specific volume is 1 over rho, right? So we can write it down as rho V here times B. So this is another way we can describe it. And also we can be here, we can have E, then we're gonna get E here. This E here is energy per mass. And then the other thing we can have, if we have mass here and we use it, then it's gonna be uh, the mass, and then here it's the momentum. So this is how we describe it. So if we, we're still gonna talk about the Reynolds transport theorem, and if we have a system at time t which consists of CV, a fluid section CV, then at time t plus del t, which is, we show the blue line here is time t plus del t, and then this, the orange line is the control surface at the time t. So then if we compare, if we see that the fluid is, the fluid is moving right from here. So we have a CV here. Let's say that this orange one right here, at the initial time, the CV and the system is going to be the same, right? So let's call this one as CV. And now when it's moving, right? And let me say that it's going to be a little further right here, right? Then if I call this regime, this regime does just right here, let me just choose another color. This region here, I'm gonna call this one I, and then the region here, I'm gonna call this one as 2, right? Then it means that right now our system is CV minus I and plus 2, right? Minus 1 and plus 2. So because we don't have this one is going to be eliminated, right, from the system because it's moving. But then when it goes on, we have this part plus this part right here. So this is how we the system is going through time. But then the control volume remains as section CV for all time. So this is a difference between CV and system. So it means that the control volume, okay, let me write it down, this is important. So the control volume remains as section CV for all time. And if we use the Reynolds transport theorem, at time t we have this formula, and then at time t plus del t we have this formula, right? And also we can have the theorem in the integral notation as well. And also we know that this part right here, this part, this is the only regime which is common between the system and control volume at time t plus del t. So let me write it down. This is the common regime between system and CV at t plus del t. We also can name this flow which is coming here as B in, and that flow that goes out at B out. So here instead of B1 t plus del t, we can write it down as B out, and this one right here can be B in. Oh, I write it vice versa. So this is B in and this is B out. And if we use some small amount of fluid mass, del m, and then we have a formula for del b, which we call it b rho del v, right? We are using that theorem again. And then if we substitute some of the formula that we already have here, we're gonna get these two formula. So I didn't go through all of the steps. So just also note that the RTT analysis has some restrictions. The restrictions, so let me just write down the restrictions here. The restrictions. So the first restriction is we have a fixed control volume. The other one is that we have only one inlet and one outlet. So also we consider uniform properties across the inlet and outlet. Across the inlet or outlet. And another one is that the velocity was normal to section 1 and 2. Another way, if we have, let's say, a pipe or I don't know, something like this here, then we have, this is our normal vector to those surfaces, right? And then also we know that when velocity is going in, is going to be to the surface, and then when it's going out, it's coming out of the surface, right? Velocity out, then velocity in. This is why right here we have a minus sign for the velocity going in, and plus sign for velocity coming out. It's because of that because of the multiple if we multiple v by n, this is how we need the velocity component normal to the opening. So in summarize, it means that we have a negative sign negative sign conversion for the inlet, and then for the outlet we have a positive sign. And also in these two figures right here, we can see the outflow across a typical portion of the control surface. And also this is the Reynolds transportorium. And if I talk about okay, let me first talk about this one. This minus sign here, sorry, this one right here. This means the same thing that I said. It's the velocity and normal, I mean the unit normal, are opposite in direction when it comes to the inlet or outlet, right? When it comes, sorry, to the inlet. Then here I'm gonna elaborate all of the terms. So this one, we know this is the time rate of change of B for the system, and also be careful that the system moves but control volume is fixed. Is fixed. This term right here is the rate of change of B within the control volume, which also represents the unsteady effects, because you know it has a time in it. And this one right here is the net flow rate of B across the control surface. So in chapter 5, we're gonna talk about control volume more, and show that how considering and assigning different control volume is important for solving the question.